저희 다시 한번 우리 러스 렌자스 매니저 만나보도록 하겠습니다. 영상으로 같이 보도록 하시죠.
Hello, my name is Russ Renzis, and I'm the Quantum Technology Market Manager at Oxford Instruments. I first got involved in quantum in 2016 when I was the Director of Device Fabrication at Rigetti Computing, which is a superconducting quantum computer company. So I had to understand how to make those devices. I've been with Oxford for about 2 years now, and Oxford Instruments is in a really unique place with quantum, as you'll see today. So I'm excited to tell you about what we're doing. We're in a whole lot of consortiums, including the Quantum Economic Development Consortium in the United States, as well as several international ones. In particular, I want to highlight two university collaborations that we have, and that's TU Eindhoven, which is in the Netherlands, and the University of Glasgow. A lot of our work in this area is in collaboration with those two universities. Oxford Instruments was started in 1959. We were the first commercial spin-out from Oxford University, and actually our first big application was the world's first superconducting magnet. In the 1980s, we joined the London Stock Exchange, and we expanded globally throughout the 1990s to our current global presence today, which continues to expand. Today, we focus both on commercial applications, established industries, photonics, power electronics, medical, lots of other areas, but also very much in the academic community. Quantum today is really transitioning between those areas. There's a lot of academic activity as well as quite a bit that's happening in industry as well, more and more every year. As I said, we're a global company, so I'm actually speaking to you here from Reno, Nevada, which is very close to our California locations. And our headquarters is in the United Kingdom, near Oxford. So let's talk about quantum devices and what they are and why you'd want one. So there's three primary categories of quantum application. The first is quantum computing. Quantum computers will not be running video games. They're not going to be replacing your Nintendo Switch. They're not going to be your computer at work. You're not going to take them on an airplane too soon. What they are is a coprocessor for specific types of extremely difficult calculations that are done on supercomputers. So this means that the applications for quantum computers are really things like simulating molecular structures, pharmaceutical drug design, that sort of thing. Of course, the most well-known application is decryption using Shor's algorithm. That's a very, very challenging application, and it's one of the ones that will be most likely one of the last for us to be able to do because of the requirements. You need to have a lot of very, very high performance qubits for that, as well as error correction. The next quantum application area is for communications, and this is really secure communications, the quantum internet, that sort of thing. And the last is quantum sensing. Quantum devices are able to sense very, very small signals at the extreme limit of noise with improved spatial and resolution and sensitivity compared to conventional technologies, classical techniques. There are also many adjacent technologies, such as single photon emitters, single photon detectors, quantum transducers, quantum amplifiers, superconducting cabling, much like building a spaceship where you develop a lot of other technologies that are useful both for the spaceship but also for other things. In quantum technologies, we're developing a lot of things for quantum computers and quantum devices that will also be useful in other areas such as classical photonics. One interesting thing about quantum is it's not just one way of making a device. There's not one kind of quantum device. You can make superconducting quantum devices. You can make Google's quantum computer was built that way, the one that's best known. Rigetti, what I worked on, was a superconducting quantum computer. There are also photonic quantum computing approaches, psi-quantum, for instance. There are ion trap quantum computer approaches. There are color center ones. This is diamond NV center, now silicon carbide, a little bit of rare earths and silicon. There are silicon spin devices. There are also cold atom devices that don't use any kind of device fabrication whatsoever. Now, a very unique thing about Oxford Instruments is that we're comprised of about 9 different business units, and of those, 6 are relevant to building a quantum computer device, making the device, measuring that device, testing that device, cryogenics for quantum devices. And these are across all of the different ways of making a quantum device. I primarily work with the plasma technology business unit, and we're the ones that have to make the device in the first place. Deposition, etch, things like that. We also have device characterization business units. These include Asylum, which does atomic force microscopy, and nanoanalysis, which does analytical techniques that work with electron microscopes. VTech is a business unit based in Germany that does vibrational spectroscopy, which is especially relevant for photonic-based techniques for quantum devices. We have Nanosciences, which is our dilution refrigerator business unit, very critical for superconducting quantum computers, as well as Andor, which does photon detection, as well as other cryogenic devices. So at the end of the day, if you're making a quantum device and you need it to work, the thing that matters more than anything else is loss. Quantum devices typically have their signal, their information encoded in a single photon, a single electron, or a single spin. And not only is it encoded in that, it's encoded in the state of that thing. In a classical device, your signal might be encoded in many photons, many electrons, many spins. If you lose some, it's okay. Don't lose all of them. In a quantum device, if you lose one, the one that your state is encoded in, that contains the information, it's a problem. So in making quantum devices, we have to think, how do we reduce loss? How do we do better than all of the ways that we make things today? This is true across all the ways of making quantum computers and quantum devices. In superconducting qubits, the information is encoded in a microwave photon that's stored in an anharmonic LC resonator, where the anharmonicity is given by the presence of a Josephson junction. In ion trap quantum computers, the information is encoded in the energy state of an ion. In a photonic quantum computer, it's the mode of each photon. In a color center based device, oftentimes for sensing, the information is encoded in a spin, nuclear or electron. First thing, you have to make your device. In plasma technology, we have a lot of experience with etching and depositing materials. We've been doing reactive ion etch and chemical vapor deposition for decades. There's 2 areas, however, that I really want to talk about that are relevant to the next generation of quantum devices with lower loss, with better performance. Those are atomic layer deposition and atomic layer etch. Atomic layer deposition is really interesting. So it turns out that you can make superconducting nitrides with very thin native oxides as compared to commonly used materials such as niobium, aluminum, and even tantalum that are used in quantum devices today. Atomic layer deposition is a very uniform technique. It's very reproducible. It's very conformal, which is useful for making superconducting vias. And you can even tune crystallinity, which is particularly interesting for next generation devices where you worry about things like quasi-particle traps and superinductance, as well as potentially even for things like superconducting nanowire single photon detectors. Atomic layer etch is really interesting because it enables us to make lower loss devices that have less damage due to 2-level systems or other defects at the surfaces and interfaces. The naive way, the simple way to think about atomic layer etch is, yes, it's very slow. Well, usually slow is not better. So what would the advantage here be? The advantage is that atomic layer etch uses much less energy. It's a much less destructive etch process. And by that I mean that in conventional etching, we amorphize surfaces, we implant argon, we have chemical diffusion of reactants. That damaged region is typically about 5 nanometers, depending on the process. Atomic layer etch, by having much lower energies, yes, it can smooth out surfaces. Yes, it's very precise, but most importantly, it results in less subsurface damage. For those of you in the quantum community, you might know the phrase two-level systems. So there are fewer two-level systems. At Oxford, we're very interested in and working on both isotropic atomic layer etch, and we're interested in approaches that do not use HF, so more user-friendly for most facilities, as well as anisotropic or directional atomic layer etch, which we do in our ICP RIE etcher. Our nanoscience business unit makes dilution refrigerators. So you have to run superconducting qubits, transmon qubits, at very low temperatures, millikelvin, 10 millikelvin, 50 millikelvin. And that's to do with the energy splitting in the anharmonic LC resonator that forms your qubit. Nanosciences has partnered with a large number of very top-level institutions and companies. They're investing in future scalable production systems, and they're making larger, more modular systems so that they're ready for the quantum devices of the future that have more qubits. Our Andor business unit is more relevant to people that are making photonic quantum devices, where they need to detect the photons at the end. They may need to do imaging. They need spectrometers in order to learn things about the performance, about the photon emission. And they're very involved in color centers and photonic quantum computing devices. VTech does vibrational spectroscopy. This is very important for when you want to learn something about your device. For instance, people that are making diamond color center devices might need to do correlative microscopy, where they have a Raman image showing them the quality of the device, that their diamond pillar or some other structure is intact, and photoluminescence to see which color centers are active. VTech also offers Cryo Raman, which is really important as a fundamental analysis technique for things like strain analysis as a function of temperature. Our nanoanalysis business unit works on electron microscopy analysis techniques. This is EDS, WDS for those of you that work in this area. And this means that you're able to see if there's a chemical contaminant or something else that might be affecting the performance of your device. Asylum makes atomic force microscopes. This is really important because, as I said, the loss in general in quantum systems is at the surfaces, at interfaces. So you need atomic scale techniques to measure atomic scale loss sources, and so that you can try to improve them. Here we're showing examples of measurements that were done on aluminum oxide to see the change in roughness versus growth, as well as on diamond to see the change in roughness as a function of etching. In general, what really makes Oxford Instruments unique in the quantum space is that we really are involved in every step of making a functioning device. To take one example, in diamond, in plasma technology, we make etchers, including atomic layer etchers. You can make your device with our products from our business unit. In Asylum and nanoanalysis, you can then measure, make sure that that device performs like you expect, that it's what you want it to be. In VTech, you can do vibrational spectroscopy to do detailed characterization and learn more detailed information, identify active NV centers, for instance. In nanoscience, you can cool to extremely low temperatures, millikelvin temperatures. This is important in diamond, for instance, if you're working with silicon vacancies. And in Andor, you can use single photon cameras and spectrometers in order to then measure the performance of your device. So Oxford Instruments as a whole is very unique in that we're offering solutions across a very wide part of what's needed to make and test quantum devices. With that, I'd like to thank you for your time, and I hope that it's a great event. I wish I could be there in person, and I hope to make it to Korea and meet many of you in the future. Thanks very much.